We're now starting the last session of the day. We have 3 talks about the LHC experiments, and we start with Alice. Wow.
Okay, thank you. So I'm going to talk about the Brazilian participation on the ALICE experiment. So I'm talking on behalf of the all the 4 institutes in their team leaders, right? So there are other countries in Latin America that take part on the ALICE experiment. I will not talk about their participation. I don't know much about them, but just to mention, there are 3 other countries that take part of ALICE. In South America, only 1 more, which is Peru. And then in Caribe, there is Cuba, and also, yes, in North America, Mexico, yes. Okay, so there's this overview. So basically, I got the white paper, and I made the white paper representation. So it's not a very fancy presentation. It's just I try to make it not very boring, but at the same time, not to lose focus of what I have to speak about. So we start with the scientific context. So Quark-Gluon plasma is still something that is very active field in high energy physics, with very strong research at RIC in the USA and in the LHC. The ALICE collaboration is the LHC experiment that focus especially in the heavy ion collisions physics. And now we have completed the ALICE-2 detector, which is the first big upgrade phase. So compared to the previous LASF4RI strategic plan, it was a plan, now it is completed. And ALICE, the main purpose of ALICE is to characterize the Quark-Gluon plasma using rare probes. And for that we will be using high rate data collection. So this was the main source of the needed upgrades that we had, because now the interaction rate is 50 kilohertz for lead-lead collisions. So we had to upgrade the tracking and particle identification systems. So basically, this new interaction rate was the main source to get better measurements and more precise measurements of some of the previous measurements that we had, but they were, let's say, not very conclusive. And now we are aiming for conclusive measurements. And so this huge amount of data and huge and enhanced interaction rate required the ALICE to be to pass through a major upgrade, because the TPC, which is the main detector system of the ALICE collaboration, simply wouldn't work with this interaction rate. So they have to completely reshape this detector, changing the multi-wire proportional chambers that were used in the TPC with GEMS. And because of the enhanced data rate, all the electronics and the way of the way that the readout the readout of the signal would change from multi-wire to GEMS, they also had to change the way that the readout would work. So it was a complete reshape of the detector. And for that, the sample chip that was developed here in Brazil, especially in the University of São Paulo, was in the core of this change. So without the sample chip, there would not have ALICE-2. So the main objectives today is, so we have this updates with our participation from Brazil and in the ALICE experiment. So what we are willing to do is to make significant contributions to quark-gluon plasma research. And objects include developing physics analysis, advanced instrumentation, particle detectors, electronics, and software infrastructure for the experiment. Another key objective is training future scientists by creating graduate level scientific projects. So one of the methodologies that we are pursuing, so we are studying the QGP or the medium created after the lead-lead collisions through few observables. One of them is the strangeness production in relativistic heavy ion collisions. So we want to see, so in principle, one of the first ideas about the strangeness production in heavy ion collisions was that they would be enhanced when compared to PP collisions. So the theoretical people, they would kill me when I say that, because they say that actually PP collisions is suppressed, is canonical suppressed, the strangeness production. So, but in fact, what you observe is that proportionally in heavy ion collisions, you should see more strangeness than we see in PP. So one of the ways that we are looking now is for the strange variants, because they are crucial. First of all, because of the enhancement, as I said, and also because we have other signatures that we would like to see in the formation of these strange variants, right? So here is just so especially what we would need to see is in the low PT regions, where the background is higher and it's more difficult to have a clean tracking and a clean signal. So we are developing here in Brazil, in the University of Campinas, machine learning algorithms to improve strange variant reconstructions, right? So here's just one of the samples. So we have this, the cascade decay in this topology, and this is the reconstruction. So we have the cascade reconstruction signal to background ratio, and we see that we have some improvement, some significant improvement with the black line compared with the traditional method in pink, and the other color, it was not so to see here, but yeah, you got idea. So it's, I think it's red, or something. Okay, so this is the main strategy of the subgroups that are looking to strangeness and strange variant measurements. So they want to focus on the development of new machine learning techniques. One of the main physics goals of this kind of analysis is to measure the lambda polarization, because lambda polarization could give you some signal. It could give you evidence of the formation of some kind of a vorticity, and this vorticity, and of course, if you have a jet would also produce vortices. So this vorticity, it would in principle thermalize with an hydrodynamic medium, and this would be an extra evidence that there is a hydrodynamical phase, right? Because this is mostly accepted, but not completely, totally accepted yet. The other family of observables that we have is the ones that we call the hard probes. So basically, the idea, we call it in general of QGP tomography, because in principle, these probes are created in the beginning of the collision because they are early produced because of the high Q square transfer. And then they pass through the medium, right? And as passing through the medium, you have an idea of what is composed of and what interactions of these probes tells us with the medium. So of course, we need to take this so-called hard probes in PP and PLED to compare with what happens in lead-lead collisions. So basically, most of the analysis that we have in the group normally work with heavy flavor and jets, and the combination of them, right? The heavy flavor jets. And most of them using JPSI and Psi2S as components of the jets. So what we would like to see is the difference, or we would like to measure the fragmentation function of these observables within the jets. And also, we would like to see, especially for the JPSIs, the interplay between suppression and recombination. So in principle, the original idea of the QGP is that the JPSIs as a molecule, they would have a separation between the quarks. And due to the dye screening, they would be phased out, they would melt, right? But for LHC energies, so you produce so much pairs of quark, or charm and anti-charm quarks, that you would then randomly choose different produce quark anti-quark pairs and fuse them and create new JPSI states. Another thing that another observable we would like to see are the so-called exotic hadrons, like the X3872, that are actually some sort of charmonium with another low mass meson that is combined in some sort of molecule, or this at least is one of the questions that we would like to answer. If they are like a 4 quark state, or if they are like a mesomolecule, right? And so the study of this, as I was saying before, the study of heavy quark jets is mainly what we would like to see is the fragmentation function of the quarks inside the jets. And more than that, we would like to see the quark to hadron fragmentation, because this has been shown by ALICE recently that this quark to hadron fragmentation for charm is not universal. So there is a difference between what happened in elementary collisions like electron-positron colliders and hadron colliders. So we have a difference in the way that this distribution of final state hadrons happens when we have different collided systems. So just some of the results that we have of the measurement with JPSI in jets. So ultra-peripheral collision is another observable. This is one of the group that is more interested in that, in principle, is people from the Rio Grande do Sul. So the idea is, so you have the ultra-peripheral collision means that you have the two lead nuclei, they will pass through each other in a distance greater than the radii, right? So the impact parameter is greater than the sum of their radii. And then they would be interacting mostly electromagnetic. But this exchange of virtual photons would be sensitive to the gluon distribution in the nuclei. So this is a way to test for the gluon saturation or the formation of a color glass condensate. One of the possible states that are formed in this kind of ultra-peripheral collisions are the JPSI photoproduction. Okay, and then with the JPSI photoproduction, we could in principle have evidence of saturation or not. And for that, we may use the focal, which is a new detector that will be built and installed in the next long shutdown on the LHC. And the idea is that we could measure this at very large rapidities where the Bjork and X values are very low. So current status and expected challenges. So several physics analysis in Run3 data are being conducted using the new ALICE analysis framework, which is called the O-square. The light flavored physics group, the one that is working with strangeness, is focusing now on the measurement of sigma decay in lambda, sigma zero decay on lambda plus photon. And this is a very challenging measurement because this photon is very, very light. It's very, very low energetic. It's on the order of 80 MeV. And they will try to measure this with pair production, right? So it will convert an electron-positron, and then you have to make a very good resolution of this invariant mass. And this is why they want to improve this V0 finder, which you will look for the V0 vertex, secondary vertex, with machine learning to improve the resolution of these photons. Heavy flavor analysis involve D0, J-psi, and lambda C plus as heavy flavor taggers for the jets. So you measure one of these observables in the final state. You can measure that with the detector very clearly, and then you reconstruct all the jets that you have in an event, and then you associate with them. And then you know that it would be tagged as heavy flavor jet. So the other part of the future expected challenges is the new upgrade for ALICE-Run4. So for the LHC-Run4. So we are participating in this new detector, this forward calorimeter named FOCO. And the idea is to test for the low Bjork and X regime, where we expect to see some signal of gluon saturation. So basically what the Brazilian team is doing now, we are conducting some simulations on the detector to see the sensitivity to isolated directed photons, as well as to define if we have the need of special triggers to avoid busy time violations. So these are some of the simulations that we're doing here in São Paulo. So the last part of this upgrade foreseen effort, or the LHC-Run5, is the so-called ALICE-3, which is basically a completely new detector. It will be emphasizing in soft phenomena in hadronic collisions. So it will require high rate capability and to utilize the full LHC luminosity. So one of the things that we would like to see is to provide photon searches and other exotic hadron measurements. So basically this is a scheme, overall schematic view of the new ALICE experiment, the LHC3. And this is basically all silicon tracking experiment with a time of flight detector with a very high timing resolution, around 20 picoseconds. And Brazilian ALICE group is actively involved in the simulations and also in the development of the time of flight system, which has some synergy with the similar upgrade that is foreseen for the Atlas experiment. And I believe Marco Leite will talk about this on his presentation. And well, what is the timeline? Surely we will do this, fulfill this timeline better than I'm doing it in my talk. And so the main goals here are the contribution for the remaining of the LHC-Run3 until the end of 2025, which may not be in 2025 anymore because LHC is considering change their schedule. So it may be until 2026. And then the preparation for Run4 during long shutdown 3. that will be, I don't know, 2026 or 2027 and 2 years ahead, where we expect to be including focal inside. And then also participation in the development of the time-of-flight system designed for ALICE-3. So construction and operation costs. So we have the MNOA around 109,000 Swiss francs in 2024 for 9 scientists. We have MNOB for the TPC and MFT detectors because of the SAMPA chip. They have, these 2 detectors have the SAMPA chip that has been developed here in Brazil. So it's 30,000 Swiss francs per year until run for ends, and an additional 10,000 Swiss francs for MNOB per year after the installation of the focal detector. We are there are ongoing HGCR rock chip. It's a complicated thing. I think I took too much coffee. It's complicated too. So that will be used in the focal pad layers, right? So we have we have a collaboration between the University of São Paulo and the University of Rio Grande do Sul that they are working with this electronic part. So the Brazilian groups will develop this common readout unity for focal. And in principle, we are going to develop this. And this will be based on FPGA processors. ALICE-3 proposal includes a time resolution detector of 20 picoseconds. I think I have already talked about this. And there is this development of the investigation of what technology is best suited for this detector, and this decision for what kind of technology is going to be decided by 2025. Computing requirements. ALICE groups have contributed to this the experiment through the SAMPA system, Sistema de Análise and Multiprocessamento Avançado, the SAMPA cluster. Sorry, it's the same name of the chip, but we are very proud of our state, so I think that this is the problem. And because SAMPA is the nickname for the state of São Paulo, actually more for the city than the state, right? But okay. And then, okay, so there is the need of 15% annual increase in the power and storage demand. And the Brazilian ALICE groups are committed to securing funds to meet the growing competing needs. Okay, so list of interested scientists in the community. So these are the names of the other PhD scientists that are working in ALICE, but were not listed in the beginning of the talk. And Alexandre Suardi, Cristiane Janke. So the first 2 mostly in data analysis, and the other 3, Cristiano Krug, Marco Brigante, working on the electronic pad CRU for the focal instrumentation, and Tiago Fiorini, which is studying the aging of the TPC gems. And this is what I had to tell.
Thank you. We are a little bit over time, but we can take one question.
Thank you for the presentation. I was wondering, I mean, the SAMPA chip has been a successful story, I would say, right?
Yes.
So, I mean, I didn't see any follow-up in your plans right now. So I was wondering.
About the SAMPA chip, you mean?
Yes.
I think that in principle, this is, as you said, it's a very successful story, which basically ended. So for the ALICE experiment, there is no follow-up on SAMPA chip. We participate and everything, but there is no other applications foreseen, at least for the ALICE experiment. There are other experiments that there are some spin-offs for the SAMPA chip. There are, I think, in at RIP, there was one of the experiments that was using someone in the JLab, maybe, I don't remember. There, I think another experiment in
Russia.
Yes, Russia. Yes, there are several places where people are just taking a bite to say, okay, it's good, works very well, let's buy some. And yeah, but for the ALICE, for this project, the Sampa is yes, is a terminated story.
No, it's a it's a paper.
All right. The next talk is online, I believe. Murilo, are you there?
Can you hear me?
Yes, we can hear you. We have to stop sharing here so that you can start sharing.
Okay.
You should have rights to share.
Oops.
Oh.
Sorry.
Just check.
Yeah, I think he's trying to share now. It's wrong.
No, it's good. It's good. Okay, so we can see your screen.
Okay. So, okay. What do you see? Do you see the first slide?
We see the first and the second slide.
Ah, okay. Okay.
Yes,
So I
fine.
share the wrong screen, I guess. Okay. That's maybe okay. That's okay. Not so good. I'm sorry. I have to share again.
Oh no.
Okay.
What about now?
Yes, that's great. Now we see your slide.
Okay,
Okay.
thanks.
So please go ahead. You have 20 minutes.
Okay, thank you for the organization of this event. I think that's a very nice opportunity for us to discuss these big projects and the groups in Latin America. So I will give, I think, a brief. Sorry, you cannot hear me?
Now we can. Please.
Maybe I have to speak louder.
Closer to the microphone.
Yes.
Let me. Yeah, that okay. What about now? Can you hear me the same thing, or is it the same thing?
It's the same. We can hear you if you keep speaking loud.
Okay, I'll speak louder.
Yes.
Sorry. So I need to share again. And then I was saying that I will present on behalf of the Brazilian group at the LHCb experiment, where we are in 3 institutes. So these are the list of people who are working on LHCb, and actually have one which is connected to Brazilian Institute, but is from Honduras, Melissa, and we are scattered in Brazil, and that's only to say how big is the Brazilian participation in the LHCb collaboration. So officially, we are 3 institutes, maybe 4 in the future. And then in terms of authors, we are 2.4% and 3.1% if you count the PhD authors. And we are the group is working in the experiment since the first proposal. I'm not covering the history of the participation of Brazilian in the experiment, but I can provide information if you have questions. I will focus now on the upgrade of the experiment, what we call upgrade 2. This is so this is a unique and opportunity, since the LHCb can provide results that, if you consider all charged stable final states for flavor physics, if you consider neutral particles, then value 2 can be competitive with LHCb, but it will be competitive. And for rare decays, this is where we can have the most precise tests. And there are several complementary studies with respect to the what we call general purpose detector. And we learned that with higher luminosities, and we have, and then we learn how to have more efficient triggers, which means that the data analysis, the results, you have a better impact, a higher impact on the physics we achieve. And just to be clear, if you look at the European strategy update, it says clearly that for high luminosity LHC, flavor physics and Quark-Gluon plasma program should be exploited. So that's in the line of what the European strategy update is looking for. I mean, concerning physics, this actually was showed, I guess, this morning in the LHC talk, where you can see that if you compare what we have now with the latest, the most 2018 result, where the run 2 was where LHCb projections were already the actual measurements were already better than the projections. And then if you compare what we expect to have, if we have a upgrade 2 of LHCb, you can see that a great improvement on these measurements. And this is very important to make sure we understand the CP violation parameters in the B system. This is just an example for which kind of precision we can have, but there are other several examples in this paper that are now published, that not only in the flavor physics but also in the electric and QCD measurements. So just to have an overview what we plan to do. So I'm assuming that you know the LHCb detector, which is probably not the best thing, but I'm just going to highlight the things that are going to be improved with the current detector. So what you see here on the left side is the vector vertex locator detector, and this is where actually the collision happens. So our detector is a forward spectrometer. So that means the collision takes place in this point in the left part of the figure, where we call vertex locator, where it's very close to the interaction. And then the particles that we basically measure the particles in the forward direction. So the value is going to be upgraded with 4D detectors with timing information. That's a necessary step for this detector. And the magnet is also updated. We have all the what we call now the might tracker upstream the detector. We have a new particle ID detector called Torch, and the calorimeter, which is going to be improved with respect to the current detector. I remember that the calorimeter for the upgrade 1 is basically the same technology. Now we're going to move to a new technology. So this is tracking a particle ID that you can see. And now going in more details, we are planning to run with 7 times more PyLab that we have right now in run 3. So that means the multiplicity are 7 times higher. For, as I said, for the tracking system, and the VLO needs a resolution information, and this is for 50 picoseconds. That's one of the areas we are already working now, trying to with the development of the technology that's going to be used here. The upstream tracker, mic tracker, is also one of the subdetectors we are involved in the upgrade. That's for the readout board, and that this is it's already also very advanced work that the Brazilian team is working. And there are now maybe there will be magnet stations for the low momentum particles. That's a new system that after the magnet you add new magnet stations specifically for try to recover low momentum particles that will be bent away the detector, so that they can go back and be measured by the upstream detectors. Concerning the PID system, we keep the read, but now with reduced pixel with SciPM. A new system called Torch, which is a time of flight, and again, this is focused on low momentum. And the calorimeter is you have now longitudinal segmentation, and that's a new feature with radiation art crystals in a region, and the muon with we keep the old multiplier in the outer region, but we changed the inner region system. So that's an overview of what has been done so far. We published the expression of interest in 2017, then the physics case 18, then the framework of TDR, and then now we are already on the phase of publishing the first TDRs, which is for the particle identification data acquisition. That's where we are also working for the real-time analysis, and we are now going for this year for the document to finalize next year the TDR of the experiment upgrade 2. So this is and all these steps have been reviewed by the LHCc as usual. So what is the status of the Brazilian participation? So we are working on the 3 projects. Of course, it's maybe different from experiment to experiment in LHC. We just have a new detector that we worked a lot on the commissioning. So this is done, but we are still learning a lot with the new detector. And but we already some of our members were already working on the VLO upgrade, as I said, for the 40 detector. The readout of the mic tracker, which is I call it the continuation of sci-fi work, and the real-time analysis with the software part of the analysis, reconstruction alignment, and everything that goes on real time. And this is already ongoing, and then we plan to participate until 2041 of the detector. That of course can be extended. That's ongoing. And then concerning the operation cost, that's around 5K Swiss francs per year. And then if you sum up everything, that around 100K per year. I just say that I guess that's something that is for common for us in Latin America, that we our challenge is to find funding for the lack to the lack of for dedicated funding for upgrades and other projects. So that's basically what I wanted to say in this workshop. I thank you for your attention, and I'm happy to take questions.
Thank you very much, Murilo. Do we have any questions online or in the room? Nope. Okay, people are maybe a little tired at the end of the day. All right, I see no questions, so thanks for coming.
Thank you.
Then we go to the last talk of the day about Atlas. Marco.
I'm pressure, right?
We'll leave the room.
That was what I'm afraid of. Right? Yeah, okay. So first, thank you, Rogério, and the organizing committee for giving us the chance to present our work on Atlas. And this will be a very short and very brief presentation on what we are doing. And of course, doesn't cover every Atlas aspects, but we focus on what we are doing here as a president team. So in order to conduct this, I'd like to answer three questions. So why we're doing this, who is doing this, which is the Atlas Brazil cluster, and how we can accomplish this through the analysis, instrumentation, and outreach activities. So the first question is why we want to do this. We have so far really no science for physics beyond the standard model on the LHC, but there's also an overwhelming and puzzling reassurance that the standard model works pretty well through the more and more precision measurements. So we want now to turn our attention to the uncharted territory of the Higgs potential. And we do this with a very appealing motivation that this analysis has a very deep connection with questions that goes beyond the particle physics and reaches really the cosmology. For example, what's the origin of universe inflation? What's the real nature of the electroweak symmetry breaking mechanism, and how we can understand the vacuum and the stability? We know that we live in this very disturbing place where we are on the verge of this matter stability on this plot of the top mass and the Higgs mass. And this is governed by this Higgs potential here. So depending on the form of the Higgs potential, we can go from stability to stability. So also it's very important that we map down these properties. And how we map this down, we have to look at the Higgs potential. We know that the LHC, high luminosity LHC, will really open a new era within present luminosity, so we can reach a very rare process and also extreme regions of the phase space. And the main priority of the high luminosity LHC will really be the probing the Higgs potential and constrain this coupling through the Higgs production measurements. And there's also, of course, significant the measurements on the Higgs production itself, but there are strong suggestions that even if you don't find any anomaly of the Higgs production, the Higgs coupling may provide us with hints of physics beyond the standard
model. And the way we do this, we use two frameworks to interpret this data that we have. One is the symbol framework, which is called Kappa framework, which basically works with the ratio of the cross sections that we have from a given process compared to the branching cross section for the standard model. And this is in the standard model, we introduced these kappas on the cross sections, and for the standard model, everything is one. And this is good if you want to spot large deviations. If you want to go deeper in this, then we have to go through another framework, which is an Higgs effective field theory. And these interpretations are a very important area where we have the interplay between the theory and the experimental community. So this is a very quick panorama of the Higgs measurements. This just brings a picture of what we know now. We have measured the Higgs boson production cross sections in different kinematic regions. This is a picture of ATLAS probing the Gluon-Gluon fusion process that produces the Higgs on different regimes, and the Higgs associated to vector bosons and the production with top quarks. So this is being mapped, will be even more mapped. We know the Higgs mass with a relatively good precision of 0.1%, and it's coupling to the many of the particles. But what is now the big question is how the Higgs couples to itself. And that's the question that we want to answer from now on. And we have been trying to answer this since the early days where we could accumulate data on the LHC. So the standard model, the Higgs production is about 1,000 smaller than a single Higgs. And the main process that the Higgs can be produced is through the Gluon-Gluon fusion and by vector boson fusion. The Gluon-Gluon fusion, it's about 25 times more higher cross section than the VBF, but both processes can probe different parts of phase space and probe different models. So it's important to use two. And we select not only ATLAS, but also CMS, those what we call the golden channels. So the Higgs in 4Bs, the Higgs in BB tau tau, and the Higgs in BB gamma gamma. And why we do this? Every channel has a relative ratio. For example, if you look at this plot here on the bottom right, you have the Higgs in 4B that has the highest cross-section production, but also it has a very challenging background. And also it's good to probe best a region of the mass when you do the resonant search. And this is a very difficult analysis, and we will be plagued by unprecedented bilateral when we go to the highland noise LHC, and this will place a lot of pressure on the detectors and the trigger of the data acquisition, and also on the modeling itself. It's not only the experiment, but the models that will try to explain this will have to be much more sophisticated for the data that we're going to have. I'm not going through this table, but the idea behind this table is that we will need to probe these three modes in order to have the complete picture, or at least to try to have a better picture of what's going on. So who will do this or participate on doing this? Of course, this is a very large analysis, very high participation inside the experiment. But in Brazil, we are 5 institutions that are spread in several states. And we had so far about 29, probably now a little bit over, PhD theses that were done on ATLAS topics. And support from several funding agencies, from the federal government, and also from the state funding agencies. So what do you do? In ATLAS, we have been covering a nice spectrum of activities of course, the physics analysis, which is the main drive for this collaboration. But we also have the working on software development for performance, trigger, and reconstruction. We have a tier 2 data processing in São Paulo that is shared with ALICE. There is instrumentation development on semiconductor sensor and electronics for calorimetry. There is participation on phase 1 and phase 2 ready projects. The tech operation is an important part of this. If you participate in an endeavor like this, you have to help your collaboration to take data, to keep the systems working, and so on. So there's a responsibility that comes from this. And there's a strong and pioneering outreach activities in high energy physics, also in Brazil, which I'll talk later. And also on the same spirit that you have to collaborate, we also have to participate on the management of the collaboration. We have until now 25 physics analysis. Most of them are completed, and we have about 4 analyses ongoing with the group on different areas. And we also provide support for other activities where where the groups were not directly involved. For example, here we help the technical coordination on the new small wheel, which there was a lot of pressure to finish this before the starting of the run 3. So we had 2 very skilled technicians helping the group there. And also we have collaboration, as Fernando has already mentioned, with Argentina and the trigger, and with Chile with the Higgs analysis. So how we do this? We do this through the analysis of the data that we take, and with the instruments that we want to build or keep upgrading for this. Okay, my arrow here is the box. Anyway, yeah, it became a box. It's transformation that I was expecting. So I start with the run 2 analysis, where there was collaboration from the Brazilian groups. And here I show the combination of these 3-4 channels. We worked on the BB Tau channel, and this turned out to be a good choice, because at the end, this the channel, I don't have a pointer here. This channel here is the one that shows the best sensitivity to the standard model strength. And you look at this coupling of the kappa lambda framework through the cross-section reduction. Atlas has shown this excess of this mass region. CMS doesn't see this. And this is something that we need to drill down, and we have to work on this for the next round of data. And most of this comes from the BB Tau channel. So now on the run 3, we, as Atlas Brazil, we are focused on again on the Higgs to BB Tau. And this analysis will start with the non-resonant dual and vector boson fusion. The resonant the signal will come later. And we have some advantages that will be very important to increase the sensitivity for this channel. We are moving to a better Pythagor, new triggers that were in place for this. Some are very specific to the signatures, and of course we have more data. There's also a significant upgrade for the Monte Carlo signal and background modeling from what we learned from the previous analysis. Some of the things are being ported now, and we changed some of the generators for the signal. So before we use CNNLO, and now we are going to Manigraph for VBF. POHEG is still the same that was used before, and Sherpa is a very new version for this, but this is for the background. There's a new analysis framework, and we're going to reanalyze run 2 and run 3 data together and move to the kappa and FT frameworks for interpretation. Another part of the work is the search of axion-like particles. There's an exotic decay of the Higgs that can go to a Z boson and an axion, and this axion will decay in a pair of very collimated photons. This makes a very nice possibility to trigger on the Z and then look for a pair of photons. And one problem on this is that this topology can lead to loss of one photon because one can be discarded as a background, and or two can be merged as one photon. So there's work that needs to be done on the calorimeter side to reconstruct these photons. So the challenge that lies ahead, Fernando has gone through this. I'm not going into details, but in brown, we have the past, in green, where we are now, and the blue is the future. And we know that 40 EV is our limit. We want to have anything more for many years to come. And there are so many questions that we have to answer. And we only took 5% only of all the LHC data. So the most of the data is still to come. And this will come with increasing number of collisions that needs to be handled with a complex topology from the PILAB, the pressure on the trigger in the data acquisition system, and very high radiation environment. So all this will need new detectors, new electronics, new methods of reconstruction, and also precise luminous determination. So we are moving from this scenario with an average number of collisions per wedge cross 50 to a scenario that's worse than that one of 140 collisions to 240 collisions. You're going to have this 240 collisions at the average 25 nanoseconds. This creates an irreducible background and will be challenging for track and vortex reconstruction. Atlas is replacing the inner tracker to inner tracker that have an extended coverage, but this inner tracker with extended coverage cannot keep the spatial resolution on the Z across the full coverage. It deteriorates as you go to the forward region. The only way that we can solve this is adding a fourth dimension in the reconstruction, which is the tide. If you look at this figure here, you have in red the hard scatter that generates the trigger, in blue the PILAB, and this, if you flatten this on XY axis, this is recognizable. If you add time, you can, with precision, you can separate this. This is what is shown by this figure. If you look only on the spatial dimension, all this is vertex in one event for PILAB of 200, and you have all this vertex. If you correlate this with time, then you have a much better situation to handle. And the way we're going to do this is with a new detector. It's a high granularity time detector. It's a state-of-the-art sensor, ultra-fast sensors, and two discs that will be placed between the barrel and the end cap of the calorimeters. These are a challenge to build. They have to be very radiation hard, and they have to keep the performance across the high luminous LHC. And we are collaborating on on several aspects of this detector. On the sensor, since the R&D, now the R&D has passed, we are in production of the sensors. And in São Paulo, we have built this facility for semiconductor sensor testing. And this is a view of one wafer. The sensors are arrays of 15 by 15 bags of 1 millimeter that will be assembled on the discs. And these will be produced, and some of the samples will be sent to São Paulo and CERN, and we will do the tests and the measurements to qualify the sensors for assembling on the detector. So the history, it's not the ends there. You have to work with this information that we have now from the sensors, and how you do this four-dimension tracking. We know that the current method that is used for reconstruction, that is a column-based filter, does not scale very well with the number of tracks. This top right plot shows how long it takes for an event as a function of the number of collisions, and this thing explodes as you go to larger mean. We need to develop new methods to do this reconstruction. Even as, for example, if you the B tagging performance relies heavily on the trigger, and this is something that needs to be done very fast at the high level trigger. It has to be not only an offline development, but this has to be ported to the high level trigger, as Fernando also mentioned before. This is done using this ACTS framework. This is a framework that was first started with an Atlas project. Now it's becoming something that is beyond the Atlas. Several initiatives for trackers beyond the highly agnostic LHC are also looking at the use of the ACTS for their analysis. And the idea is to do the simulation. The ITK and the GTD is already on the geometry envelope for the ITK. And in the future, what we want to do is to develop methods that can be run on heterogeneous architecture. That will be probably the only solution if you want to do this with the time budget that you have. Another development comes on the calorimeter side. It's the Murilo Rangel calorimeter, which brings the information of the ring around the cell with maximum energy. So this profits from the outstanding performance that we have on the Atlas Argon calorimeter, and that it started with electrons and it's now being ported to photons. It has a high background rejection at the very early high-level trigger stage, and it has the potential to outperform some traditional methods that we have. And this was recently introduced on the rotary trigger medium. And this is the figure that Fernando again showed in Atlas, and represents the information flow inside the proposed trigger for the phase 2 of Atlas. And one of the challenges here is how you bring to this flow the algorithms that we have, and make sure that they perform well. We are bound by the two constraints, which is low latency and parallelization. And the best way to do this is implement this on reconfigurable logic. And this is a work that is being done by the people from Argentina and people from Bahia that are working on the rigor side of this, that shows this nice collaboration between the two institutions. Finally, there is also signal processing for the hadron calorimeter. This shows a method that was proposed by one of the groups in our cluster. And this plot shows the error that you have on the energy estimation as a function of the eta position of the calorimeter. And this is for a lap of 200. The open markers are for this new method that provides a smaller error than the conventional ones. So this is a very good candidate to be implemented for the highly luminosity LHC. So this brings us to the outreach. Outreach is a very serious activity that in Atlas, since the early days, have been the groups have been taking part of this. This brings the Atlas scientists, and since 2011, we have probably several thousand of students and teachers that have been going through this. For example, this year, there was only in one event 300 students, and this is becoming increasingly a challenge to work with this. And this is deeply rooted with the IPUG activities. Many states in Brazil are now participating in this, and this is basically done in person. At the early days, persons were trained, and now they can do the master class and the video conference with CERN at the last day. There is also the virtual visits, which is fully online, where we have the students here in one university or institution, and they connect to someone at CERN that shows them the experiment, they answer questions, and there's an interaction with the people here and the person there at CERN, since they cannot go to CERN. And there's a large number of students that participate on this. And this has been a very important part of the outreach activities in Atlas. This is just a slide that shows consolidated information on the participation. I didn't cover everything. There's computing that it's even though if you compare with the Atlas number of machines on the grid, it's small, but it is also something that is important to contribute to the experiment. There is also analysis on the procedural measurements on the standard model that's not covered here, but we will now start in more and more focus on the HECAP, which is a huge enterprise, and we'll need all the efforts on this analysis. So I think that's it. We know that the LHC will be our next playground, and we cannot leave any stone unturned for that. And that's it. Thank you. Yep.
Thank you. Questions for Marco?
So I have a question. At
Yeah.
the end of LHC high looming, what is the precision we're going to measure double Higgs cross-section?
That's a good question. I saw this number and I don't know even if we'll be able to really measure.
Okay.
I think that we can set a limit
Okay.
on this above the standard model.
Okay.
No, I'm not sure. It's hard to make these
Yeah.
projections, of course,
Yes.
but I thought we were aiming for at least evidence.
Evidence.
Combined.
Yeah.
You know,
So
so
3 sigma.
which means that it's more than 1 sigma. So yeah, you can call that a measurement.
Okay.
You can sometimes even call something a measurement if it's not yet
Right.
even 1 sigma. That's cheating a little bit.
Yeah.
So it's very difficult.
Yeah, I think that the real measurements on this will come up.
But so far, as you pointed out, we have been doing already much better than we expected.
Yes.
So and we keep trying.
AI, which is the magic word.
Yeah, you have to use you have to say AI instead of machine learning now.
Yeah, I don't know. I think that you see, for example, Bitagi shows a significant increase in performance.
Yes.
I mean, significant. It's like depending on the phase space, it's I think it's between 7 to
Yes.
almost 20%. It looks small, but the impact on the analysis itself is huge.
In some cases, have been much more significant than that, like a factor 2 for boosted
Yeah.
topologies or
Yeah.
more. And
But then we have to be a little bit careful when we do this with the B, because there's this discussion on how this can affect really the bias, the result. I don't know. I think there will be a lot to learn for these next years.
And 4 gammas is totally out of question, right? It's too rare.
So it's 0.7 times 0.7. It's gonna be like possible.
Even with 3000 inverse femtoforms.
I don't know how many events you need to expect.
Okay. We can calculate this over years.
Gammas are also not background 3. So.
Okay.
If there are no questions or comments in the room or online, I would like to thank all the speakers of this afternoon session.
For those that are here in presence, we're going to have dinner at the Movino.